All right, so everything right here, there's nine. Yes, there's nine problems. A lot of them becomes just plugging them in, and so really the hardest thing about these problems is really identifying what um, what the picture looks like. And I hope that if we can talk about the picture as well as any constants, um, that's what's the most going to be most helpful for us. I don't want to go beyond any of that. I don't want to identify the variables and identify the formulas. I just want to really work on identifying the the diagram during this time. So, and here we have a rectangular wall, a well, sorry, 6 feet long, 4 feet wide, 8 feet deep. If water is running into the well at the rate of 3 cubic feet per second, how fast is the water rising? Now, keep in mind that which variables are constant and which variables are changing. All right, so I think a lot of the problem that people get here is that this is what I consider a static structure. So the structure itself that in which the related rates is happening to is solid, or it's a solid structure. However, we're not looking at that solid structure. We're looking at some liquid or some type of material that is going into that structure. So in this case, it's a well. Um, so what I want to see is how is this how what where we're work the liquid in this case is water. Where the material we have is water, and it's slowly going up. So while the well is 8 feet deep, the height of the water is not 8 feet. The height of the water is whatever the height of the water is at any point in time. All right. So what type of shape do I have here? What is the geometric shape that I have that I know the formula for and so forth?
A rectangle.
No, it is not a rectangle. It is not a cylinder. A well is not a geometric shape. I said no to Norda because she gave me a two-dimensional shape. This is not two-dimensional.
Oh, is it a rectangular prism?
A rectangular prism. There we go. So when I'm thinking of this shape, and just to be a little bit more accurate, we have a rectangular prism, and we have the width, the length, and the height. And what's happening here is that water is being poured into here. And so we have water that is in this well. And so I actually this letter H is not actually relevant here. We would refer to this as sorry. We refer to this as, I like to call it big H, because what we are really looking at is little h right in here. Now, in addition to this, we know certain things are constants. So and we're talking about our constants, our length, is our length constant or changing? It's gonna be a really long class. If I get people that don't participate in terms of this one, it can be really long. Or I can get through all the problems, or I could just send you guys off on your problems and just do it on homework. It's a well. What is constant? Is length constant?
For the rectangular prism, the length is, yeah.
The length is constant.
Fixed.
It is fixed. Length is constant. So L is 6 and width is,
4.
well, it's constant.
Yeah.
Width is 4. And height, what about height?
For like the whole rectangular prism is
Oh, no.
constant at 8.
Oh, okay, so but we're not going to even use that. That's what I'm trying to say. Like in this case, we're never going to. It's actually extraneous information. What is the only what is the little height of the is the height of the water changing?
Yeah.
Yeah. So the height of the water is going up. So h is our only variable of t. So h is a function of time, and of course we have our dv dt, right? That's going right into here. So my only variable in this problem is h of t. dv dt is going in at a constant rate of 3 cubic feet per second, and so we know what dv dt is. We know the value of dv dt. Now remember, dv dt is the volume is not constant, so volume is increasing as well. So actually, technically, volume is also a function of t, where L is 6 and the width is 4. Okay, so that helps you do it so that you don't have to do a triple product rule. Remember the idea that if a function is constant, we want to utilize those and plugging them in. All right, next problem. Superman is in level flight. I mean, you're good. You finished it out there. That's what your homework is, of course. Superman is in a level flight 6 miles above the ground. Okay, so visually here, if this is the ground, then Superman, well, it's 6 miles above. His flight takes him directly over BCLA. So, we have a little dot right here, and that's BCLA. How fast is he flying when the distance between him and BCLA is exactly 10 miles and the distance is increasing at the rate of 40 meters or miles per hour? So the idea is Superman is not directly above, or his flight plan will take him directly above, but he is not currently right above. So Superman is right here. So here's Superman. There's BCLA. And what we have here, and so I like to draw this picture like this, is that Superman is right here. Okay? And we have, of course, the height, or I like to call it the y, right there. We have x, left and right, and we have z right here. Now, let's ask ourselves what is constant and what is changing. Is Z changing as time goes on? Is Z a function of time? So if Superman is right there, Superman keeps flying, will X, will Z, what changes and what stays the same? So Superman is flying like that. What happens to X? Does it stay constant? Does it increase? Does it decrease?
Increase.
Yeah, so X will increase. What about Z?
Increase.
It'll increase over time. And what about Y?
Stay constant.
It'll stay constant. Perfect. All right, so Y is a constant at 6 miles. X is a function of time, and Z is a function of time. Of course, the relationship between these three variables is what? What is the formula?
X squared plus Y.
Yeah. So the Pythagorean theorem. Perfect. Yeah. So when it says, so the trickiest part here in this problem says when the distance between him and BCLA is increasing at a rate of 40 miles per hour. So I'm not going to write it down here, but what are they telling me? It's a rate because it's miles per hour. So what are they telling me? What rate or what variable are they telling me? So let's first also go. It says the distance between Superman and BCLA is 10 miles. So what are they saying? At the instant, what is 10? No.
The distance already between them?
Yes, which is? It's a no, what is the variable?
For the rate of 40?
No, the 10. The 10 miles. That's well, there's only two variables, so when you guess one and it's not right, it leaves only one variable left. And so this is the distance between Superman and BCLA. It's talking about the hypotenuse. It's telling you that Z is 10. So we're looking at the instant when we plug in that Z is 10. And what is, when it says, and it is increasing by 40 miles per hour, what are they telling you?
The dx dt?
No. They just said the distance, and we just confirmed that the distance is Z.
Mm-hmm.
So
the dz dt?
dz dt, correct. They do not tell me X. So a lot of you and some of you, I mean, the hardest thing here is you got to really practice in terms of, it's, I don't want to say it's common sense, but it's the fact that we got to look at, something as straightforward as when it says the distance. So if this is the letter and then it says something like miles per hour, you know that we said that this is Z, so therefore this has to be dz dt. And there's a lot of things. If it's miles per hour, which is a rate, you should never be labeling that as a letter. You better make sure you're labeling that as a rate. Now, this question is asking, what is it trying to ask you to find? How fast is Superman flying? So what are you trying to locate in this problem? Fast is a rate.
Would it be the dx dt?
Bx dt, correct. Now this is a very similar problem right here. This problem is very, very similar, except for what is constant and what is changing. Is and actually this problem right here is basically identical. All right, so the kite is always 120 feet above. All right, so this this right here is y, x, and z. This, though, once again, this is a constant, and the string is being pulled out at a rate um, of 30 feet per minute. And what is the length? And the length of the street is 150. So this problem right here, I want to say, is really just a follow-up to the problem up top. It is basically the identical question. Now, sometimes with the kite problem, there's various different things that go with the kite problem. In this case, the kite is always going to be a height of 120. Sometimes the z itself is constant, like the ladder, or when you get these problems, you get the ladder, which is constant, or you get the height that is constant with that problem. So I want you to really work on that one on your own. I think you can follow from problem 2 and how to do that one. How fast does the radius of a spherical soap change when you blow air into the rate of 10 cubic centimeters per second? What type of shape are we working on here?
A sphere.
A sphere. And we're looking more specifically at what formula for the sphere? When you blow air into it, 10 cubic centimeters per second. What variable or what rate is that now? I'm gonna have to put a timer on you guys. If I don't hear anything after like 10 seconds, I'm moving on to the next question. And now I've got
Volume.
3 people that's been participating so far. What is it?
Volume.
No, it is not volume.
Area.
It's dV dt, people. dV dt. What variable? It's the rate of volume. All right. Major point right here. When you see this per second, it tells you that it's a rate. It's not a volume. It's a rate. Okay. 5. How fast does the water level drop in a cylindrical tank? Okay, that's important. It's a tank, which means it's solid walls. A radius 6 feet is drained at the rate of 3 cubic feet per minute. First off, let's see if we've learned what is this 3 cubic feet per minute.
Is this one the dv dt?
That's a dV dt. Perfect. What is my shape that I'm looking at in this problem?
Cylinder.
Cylinder. Okay, and a cylinder has a radius, and it's the trick here though is that we're not really looking at the cylindrical tank. We're really looking at the water that's inside this tank right here. So, and I'm actually going to go from right here. This is the radius, and this is the height of the water. All right. What is constant in this problem? Is there anything constant in this problem? Radius.
The radius?
Yes. Because it's a tank, the radius is constant. All right. And so H is really a function of T. And of course, V is a function of time as well. Volume is changing. In this case, the water is flowing out. All right. So the water is going out. So in this case, dH dt, our height is decreasing and the volume is decreasing because the water level is dropping. The water is being drained. So it just flips the signs of the answer. A spherical Tootsie Roll pop you're enjoying is giving a volume at a steady rate of 0.25 cubic inches per minute. All right, what shape are we using? Sphere. And once again, inches cubed per minute, which means that 0.25 is
280T.
Now this one's interesting because it says, and the radius is decreasing. How fast is the radius decreasing? So it's asking for the rate of radius, and they give me 0.25 inches across. What do they give me here? This is what makes this problem a little bit trickier.
The diameter.
Diameter. A rowboat is pulled toward a dock from the bow through a ring in the dock, 6 feet above the bow. If the rope is holding at 2 feet per second, how fast? So this is basically one of the same things. So the triangle problem is the most prevalent problem that shows up on the AP exam. So I put it down there multiple times. I'm going to leave 7 to you. If you've done those other 2 problems, this one should be relatively much the same. It's the Superman, it's the kite problem, just flipped inversely. The volume of a cone of radius r, height h, is given by this volume formula. So remember, when I tell you we get into these tricky volumes, they sometimes give me the formula. If the radius and height are both increasing at a constant rate, all right, so now we have volume, radius, and height. Well, volume is a function of time, radius is a function of time, and height is a function of time. This is a very traditional problem. You're given, just as you've done this problem on your homework, you have volume and nothing is constant. They give you they give you every piece of information you need to do this problem. So they give you dRdt, they give you dHdt, they give you the height, and they give you the radius. So there's nothing special about this problem. It's a cone with a radius and a height. Okay, I like to draw my cones upside down like an ice cream cone. A right cylindrical cone, okay, we have another cone, same volume formula, but has a fixed height of 20. All right, so what does that mean about height?
It equals 20.
Okay, but what does that mean about height?
It's constant.
It's constant. Okay, so it's not a function of time. So volume is a function of time, and they give me cubic meters, tells me volume per second. So that, of course, that's my dv/dt. And we know that the radius is a function of time. One of the variables has to be in it. And we know that height is just always 20. So we can plug in the 20. So we do not need a product rule on this problem. Now, if you choose to do problem 9, like problem 8, then you would have to do the whole thing with dH/dt is 0. My always recommendation that is identifying any constants so that you can plug in any constants into your equation to do it. All right, so, like I said, problems 2, 3, and 7 are near identical. The one related rates problem that I've seen pop up on the AP exam that was completely just a related rates problem was a triangle problem. There's more parts to it, but I'm going to bring that until tomorrow. In tomorrow's question, we're going to focus a lot on the right triangle again. So I put an extra couple of problems on the right triangle on here because in tomorrow's problems, you're going to do these same types of questions as a subset question, and I'm going to introduce to you a new wrinkle in the right triangle problem for this. So get ahead on the homework. Nothing really new. This was basically going to be a one-day lesson, but I extended it in terms of 2 to get you both a Delta Math practice and to get you running through in terms of going through the handout. The Delta Math was just kind of something that I wanted to throw in there extra. So we expanded the amount of time. We doubled the amount of time in terms of doing this type of lesson. Take advantage of that. Get your problems correctly done. Solutions will be posted tomorrow at the beginning in the morning at 8 after you've turned in your homework. Get your homeworks in time. Those of you who are not turning in your homework handouts in time, expect your term 2 grade to suffer significantly. That if you're not turning in your homework handouts, which there's some of you that are like, I can do the Delta Math, but I'm not going to do the homework handouts. Note that your grade is going to suffer much more this term as we're going into it, as we are getting to do these a little bit more, especially when I'm going to be giving you the next, once again, just over about 20 minutes of time to work on this handout. So work on, finding your formulas. I didn't state any formulas for you. I walked you through them. State the formulas, plug in any constants, find your rate of change formula, and after that, simply plug in the information that is given, and that's what comes with these problems. That is all I have for you today. Hopefully, I've been trying to take it a little bit easier these last couple of days. Tomorrow we have, I'm going to introduce, like I said, a new type of related rates problem that is an expansion of the right triangle. And then I have on Thursday the introduction of the last type of problem, which is technically an expansion of a right triangle, but also is focused on a cone volume. That's what I have for you.